Hello, my name is Max. I'm currently a DevOps engineer at Wargaming, Nicosia. Today I will introduce my BunnyShell DevPost Hackathon project called All-in Toolset. So what is it? All-in Toolset allows to quickly deploy complex ephemeral environments for development purposes to make the programmer's life easier. That's doable using modern and efficient logs management, error tracking, monitoring, tracing tools, and even ingress as a service tools. Of course, with the help of BunnyShell solutions. My all-in toolset consists of 5 essential application stacks. Let's go through them in order. First, I'll explain the theoretical part of each one, and then we'll move right into a practical example of deploying and using it in a real-world-like scenarios with BunnyShell templates. The first stack is about logging management. Often developers want to see logs in a more instrumentally armed way, not just through terminal or text files grepping them. That's why it's created. Grafana is responsible for the flexible logs presentation, Loki for fastly accessible and lightweight storage, and Vector for well-known high-performance processing. Let's deploy this particular BunnyShell stack and see how it works. So I already added the all-in toolset template to the BunnyShell system. As you can see, there are a variety of stacks. We'll touch them a bit later. Now, we are about to deploy log management stack, including before-mentioned Grafana, Loki, and Vector tools. Let's call it log management tools and proceed. We're happy with default configuration, so let's click the deploy button and deploy all things to BunnyShell built-in cluster. Now it's deployed. Let's check out our public addresses and then open the Grafana one. As we just confirmed, Grafana works well. Next, we'll redirect logs from our sample app to the Vector processor for easier log browsing in Grafana. As part of my toolset, I also generated multiple examples to demonstrate how each stack works. Now you see the simple user registration app, more like a snippet. The example aims to send each line of logs the app generates to the Vector instance. Now important part. Under the hood, Vector, in its turn, will process those logs and sends them to Loki. Eventually, Grafana will show logs to us, fetching them from Loki. I have to mention that on code side, this can be simply accomplished by adding HTTP handler to standard Python logging module. Not a big deal. So, all I need now is to change vectors and point to the relevant one and run the Python script. Let's do it and run a curl command to simulate an HTTP request to our application. Therefore, to generate some logs. Yeah, we've got successful response. Let's open browser and check logs out with Grafana. So, let's move to the Grafana Explorer page and construct a logcal query to perform a request and figure out some information about our curl request. Logcal is a more powerful, flexible language that includes the good old grep, regex, and some new operators for advanced filtering. Now I'm entering the label with the environment, and it immediately shows us all records for a specified time frame. I'm using the JSON operator to parse JSON logs and, that way, to show all available fields. We now see technical data like Python file name, the function called thread module, even event line number, and traditional logs data like timestamp, level, message, and so forth. Due to its time series nature, the Loki engine works fast. At the same time, Loki considered lightweight compared with Elasticsearch, so it doesn't consume many resources. There are many benefits of utilizing this stack. I don't have enough time to show it in this presentation. You can find more on Grafana and Loki's official documentation websites. And, if you're interested in custom logging processing and creating labels for Loki to do searches faster and optimize your developer experience to new heights, also visit the Vector documentation. The following stack is about error tracking, diagnosing, fixing, and optimizing the performance of the developer's code. Opinionatedly, Sentry is one of the top products on the market. Sentry comes with inherent storage components like Postgres for persistent and Redis for in-memory storage. Let's deploy this error tracking stack and dive into an example. Now all services are ready, meaning it's deployed. Let's follow the only public address available and log into the Sentry platform. We use predefined credentials that can be changed after login. Due to the hackathon's essence, I devoted little time to security, which is the part that must be improved eventually. Also, as you noticed, I used the old version of Sentry. I explained the motivation for this decision in the template's README file. So, Sentry requires the project to be created to receive anything from the application. For diversity, I decided to write example in Rust language. I created a Sentry project and got Sentry data source name. Our Rust application example will use this address to send events. It's time to run the application. The application's main task is to process a file. However, in our hypothetical scenario, the file is missing. Therefore, the application will cause a specific error and send it to Sentry. As you can observe in the source code, we need to specify the Sentry data source name environment variable to send an error event. We're executing binary utilizing the Cargo Rust manager. Finally, we got a log message saying the exception was sent to Sentry. On the Sentry side, we promptly notice that it displays an unresolved issue connected to the project associated with our application example. Clicking on it reveals a comprehensive set of fields that provide valuable information for troubleshooting the error. These fields include stack traces, error messages, contextual data, and other relevant details that can help developers pinpoint and resolve the issue effectively. Once again, the realm of Sentry lies beyond the scope of this video. If you're interested, you can always delve into official sources to learn more about it. The next set of tools focuses on distributed tracing and telemetry-based observability that provides comprehensive insights into application behavior. OpenTelemetry seamlessly collects telemetry data from applications, automatically generating spans and sending them to Jaeger and Zipkin. Jaeger enables you to picture the entire request journey. Also, Jaeger provides interactive visualizations, detailed traces, and vast insights into latency, dependencies, and performance bottlenecks. And Zipkin complements Jaeger by offering an alternative user interface for trace analysis. Let's deploy this stack and see what public addresses we'll get. As we can see, there are 4 addresses. One is Jaeger UI, one is Zipkin UI, and one is the OpenTelemetry connector for our application. And the last is the Jaeger collector if we want to send Jaeger vendor spans directly to Jaeger, bypassing OpenTelemetry. Today's example language is JavaScript. It simply simulates a primitive web server that must fetch something from a database and return data. Let's start the application web server and make a curl request to fetch some values. These values also will be sent to OpenTelemetry as a span object for further analysis. Going to Jaeger UI, we must choose the service we set in our OpenTelemetry library. We can always filter traces by various parameters or click Find Traces. As we can see, there is Get Customer Span with the attributes we added in the source code before. Alternatively, you can browse span objects via Zipkin. It works almost in the same way. Zipkin and Jaeger tools have benefits and drawbacks, like supported languages, frameworks and libraries integration, active community, and so forth. It's a trade-off and the reason why the stack was created. You can choose whatever tool you find attractive or satisfies your needs. The following stack is all about monitoring. The Prometheus, Push Gateway, and Grafana synergy is a robust solution for real-time collecting and visualizing metrics. It works relatively simply. Application pushes metrics to Push Gateway endpoint. Immediately, Push Gateway starts broadcasting these metrics. Next, Prometheus scrapes metrics from Push Gateway and stores them as time series data. Finally, Grafana connects to the Prometheus data source so you can browse or visualize metrics. If you are still struggling to get how it works for this particular stack or any other, I made a component diagram to make it understand better. You can find diagram for any stack I created in the corresponding templates folder inside the All-in Toolset Git repository. Let's proceed with deploying our 4th stack, which we will call the monitoring stack. As before, it will take some time to be colored in green. It's green now. Let's check 2 addresses we need. Prometheus. In Grafana, Grafana is the same BunnyShell component as we used for log management stack. Why can't developers use this stack and all previous ones locally? This is a good question. Yes, they can, but at least they will require more configuration and maintenance, and of course, those stacks will consume the computer's resources. Also, you can organize teamwork by sharing links to services with your coworkers. Let's examine another example and envision a rare but engaging situation where we need to collect metrics for a specific purpose. Suppose we suspect that our locally installed Spotify daemon is leaking memory. We armed ourselves with tools like PS and VMMap and started the investigation. However, we need more observability regarding graphs and data in the context of time intervals. That's why we created an advanced bash script. The script gets some unusual memory type metrics like stack, shared, mapped, and unused memories with the help of tools like PS and VMMap. Then it sends them to our push gateway in a loop. After some time, we open Prometheus to get metrics values quickly or use comprehensive Grafana dashboards to visualize metrics in the way we need and probably figure out the issue. Introducing the Ingress as a Service tool at last. It's not even a stack. These are just a couple of tools designed to help developers expose their local applications. Chisel is a fast TCP, UDP tunnel transported over HTTP and secured by our SSH. It includes both client and server, which make it easy to use. Hopscotch is a modern API development ecosystem that helps to test just exposed applications. Let's deploy this template and finally play with our last example. Among all public addresses provided, we need the Chisel server address. Now we're going to start locally in Docker a random Nginx application. It can be any application that any developer can expose, but let's focus on simplicity for now. We're confirming that it's exposed and working on port 80. Next, let's start another Docker container called Chisel Client and create a reverse tunnel between Chisel server hosted on BunnyShell infrastructure and the local Nginx server we started before on a local computer. Docker container says it's connected, meaning that it works. Let's now open another public address called Chisel Tunnel and make sure that our service is really exposed to the internet. In conclusion, we can open the Hopscotch API tool and perform different HTTP requests to our exposed application to ensure it works as expected. We only need to copy the tunnel's address and use it as an endpoint on the Hopscotch side. And that's what it is for now. Thanks for watching.